Hello everyone, welcome again to System on Chip Co-Design and Verification Elect 1002. It's nice to meet you again. Hope everything is doing well at your end and I hope we stay in contact. Please join our Facebook group so that we can discuss more of your problems on the group. Anyway, today we are going to concentrate on task scheduling. The idea that we're still concentrating on is the software or the system senses. What we are concentrating on now, the hardware senses or the system senses, how to build the hardware and the software. The problem now is the following. If I have a set of applications, and this set of applications can be presented as this task graph with V1, V2, and so on. Each of these tasks take a certain delay. So how can we present this or how can we scheduling these problems or map the applications to the processor in a proper scheduling technique and a target architecture to maximize the performance, keep the deadline, minimizing cost and energy consumption. The idea is pretty simple. I have a timeline and I want this task to be uh, mapped on it so that we decrease the deadline or respect the deadline of all the tasks. Between scheduling is very important. Scheduling is used in two things. First, is used to execute different tasks, and also it's used in the communication to set the task priority which is going to be sent and how long it will take, all the transactions, so that there is no blocking or no problem with the schedule. There's different types of schedule. There's hard deadlines and soft deadline scheduling. Soft deadlines can be broken. This is our project deadlines. Doctor, we need 1 week extra, then it's a soft deadline. I can increase it for 2 days or a week or so on. But hard deadlines cannot be broken. In system on a chip, all deadlines are hard. There is no soft deadline. Then there is two types of hard deadlines or tasks in the hard deadlines: periodic and aperiodic. The periodic tasks come in a synchronous way or a periodic way. It's called the job. Every 2 seconds you will get it. Every 3 seconds you will get it, but it's periodic. It comes regularly on regular times. On the other hand, asynchronous or aperiodic tasks come out of a sudden. There is something else or unpredictable time tasks called sporadic, which is a way which tasks that come very far from each other. But now we are going periodic and aperiodic is what we are concentrating on. Finally, we have preemptive tasks and non-preemptive tasks. Non-preemptive tasks are tasks that executed until they are done. No matter what comes behind around them, it will keep going until it's done first. Preemptive tasks, uh, if they come, they will stop others and take their places. They have a higher priority. And usually we do this if some tasks have very long execution time compared to others. So this is the difference between non-preemptive and preemptive tasks. Finally, we have dynamic scheduling and static scheduling. I'll give you an example where we use dynamic scheduling and static scheduling. If we are building a game, for instance, then schedule have to be dynamic because the game changes fast. And according to the game, the processors in your PlayStation, for instance, are going to schedule the new tasks. So this is why PlayStation 4 got one processor that builds the new schedules automatically for other processors. On the other hand, on simple systems or on systems like us, like our systems that we have, we know that systems before we start, there usually things are static scheduling. Static scheduling taking a prior knowledge about arrival time, execution times, and deadlines into account. Dispatcher allocates processor when interrupted by timer controlled by a time generated at design time. This is what we are going to concentrate on and what we are going to discuss. We are not concentrated on dynamic scheduling. Between this is important also in embedded system design because a lot of people teach scheduling as real-time operating systems or real-time RTOS, Anyway, are we going to distribute the tasks on one processor or on multi-processors? Actually, in our course, we are going to concentrate on one processor, on a monoprocessor. But if you have more multiple processor, you have to learn how to define or how to schedule things on multi-processor. This is the first thing we need to know. Is our task schedulable or not? If your task is not scheduled, you will have to uh, realize this, and you have to either change your tasks and constraints or to add more processor. So you need to have sufficient tests and necessary tests to ensure that your tasks are scheduling and your scheduler is right. Usually we do this by calculating a cost function. The cost function is a function that maximizes the lateness. If the function is be a maximum of all tasks, this is the definition, we are going to maximize the completion time minus the deadline of all tasks. This means that we are going to finish in time. If we didn't do so, we are always in trouble. So anyway, if I have two tasks like T1 and T2 start together, I have this notation that this is the time the function is executed, this is the next one, this is the third one, and this T2 starts from here, and so on. If I have one processor, I have to choose between task 1 and task 2, which one or which job should be executed first, and so on. A schedule is defined to be optimal if and only if it will find a schedule if one new task exists. Anyway, let's first concentrate on periodic scheduling. So think about this. This is the period P of I, and I have D, which is the deadline interval. If the task starts here, it has to finish before this. The C is the computational or the execution time need between the start of the task and the end of it. And the laxity or the slag is the time between the deadline and the execution time need. So I have period, I have D, I have C, and I have L. My main task is to finish all tasks, all C before the D. This is a very first thing. So there is a very important rule, which is the root monotonic rule or the average utilization. This is the average utilization of a system, which is the mu. It's called the sum of all tasks. The computational time, the mu is the sum of, the sum of all the task computational time divided by its periods. If you have mu, which is less than m, which is the number of processors, you are safe. Okay? For instance, think about this. If you have 10 tasks, each task will take 5% of the system. So 10 multiplied by 5%, then your utilization is going to be 50%. This calculates by the computational time divided by the whole period of each time. So if each task is going to be executed in 5/100, then it will be scheduled over one processor. If you have 10 tasks, but each task takes 12%, this is 120%, then your tasks are never schedulable. Anyway, this is an important rule, and then Leo in 1973 proved something very important. Proved something called rate monotonic tasks. If I have totally independent tasks and all the deadline of the task should only end before its period. C is constant for all known tasks, or is a combinational time for all execution time for all the tasks. Please make sure that your mu, your utilization, is less than or equal n multiplied 2/1 of n minus 1. This rule is extremely important. Why? This rule indicates simply that if you have more than one task in the processor, then you cannot push the utilization of your processor to 100%. For instance, if you have only one task, your utilization of the processor should or can go to 100%, which is the one. As soon as you have two tasks, your utilization should not exceed 82%. Three tasks, 78%, and so on. If this tends to infinity, then think of it as a Len2 equation. Okay, this will explain something very important. Think of this, a small microcontroller that you have two or three tasks on it. Sometimes while it is running and it's moving well, you find that one of these tasks slips. The problem with this is that if utilization is more than 82%, in most of the times it keeps running smoothly. But after a while, sometimes it will fail and you will never know what's your error. I've seen this more than 10 times. You have a project, it's running smoothly, then it fails at some point, then it works again smoothly. Let's see why. If we have three tasks like this, and T1 is faster, it comes with a smaller period than T2 and T3, then it preempts the other. T2 and T3 are equal. Okay, and T1 got a period of 5 and execution time of 3. T2 got a period time of 8 and execution time of 3 as well. So T1 will always preempt task 2. If we think about this rule, we'll find the following, that my utilization is 0.975, which is more than 0.828, which is the limit by Lee. Let's think about it. The worst case always happens if T1 and T2 get in the same time. So when T1 waits for 1, 2, 3 time period, it will preempt T2, then T2 will start 1, 2, T1 is going to come again, and it needs 1, 2, 3 time periods or time slots before this T2 ends. That deadline of T2 will arrive, then you fail to execute T2. What's the problem? That if both deadlines if both periods did not start in the same time, you will notice the following: that T1 will end, T2 will end, T1 will end, T2 will end, and so on, until by chance we have this awful case again, which can happen anytime that you don't know. So think about it like this is the same description, but let's say about a critical instance, or this is the definition for you to define your system. The critical instance of this system occurs if the task is simultaneously released with all higher priority tasks. Because your important task, if you have n tasks, and T1 is more important than Tn, you are going to be delayed over and over and over again until T1, T2, and so on. When it finishes, then Tn might fail. What we'll do now is that we will go to prove how critical tasks are important with them. Think about this. If Ti is delayed than Tn, we don't have a problem with this. But if Ti and Ti plus 1 and Ti plus 2 and so on starts together, then you might fail to execute such task. There is a complete proof of the RM theorem here. I'm not going to go to this proof, it's just for your knowledge only. Just like there's two cases where C1 is less than B2 minus F of B1, and the other case where C1 is bigger than B2 minus F multiply B1. Please go through it. If you have any questions, let me know. But anyway, it is not in the exam. It's just like to describe or to see how we reached this for two tasks. So, as a rule of thumb, the properties of RM scheduling is based on static priorities. Always faster or more or tasks with faster period got better priority, and take care that we have always to respect this law. If you don't learn anything from this lecture except this equation, then I did my job. This equation is essential in hardware design, and it is essential in embedded systems. Remember to use this equation if you are choosing between processors. This is essential. Okay? Anyway, we'll go on more. And we think about aperiodic scheduling. Scheduling with no procedure constraints. If scheduling here, we don't have a period, but we have only a deadline. So you have a deadline, you have latency or slack, and we have the execution time. We don't have a period that this will come. You might have different uh, instances of this, but of course after the deadline, like you have one here and one that can start here. But you don't have a laxity or you don't have a period. This is a periodic scheduling. Okay, this is very interesting. All different types of aperiodic scheduling still respects the RM law. So if you ever cross the RM law in aperiodic scheduling, make sure that you are going to fail as well. Yet, here, preemption is useless. So we define something called earliest due dates. If you have 3 tasks, don't care about the time, but care about which one will come the earliest deadline first. So if it is this green, yellow, and blue tasks, think which is the fastest one to finish. This one to finish, then I will start with it. Then this one and this one. This is the only way to ensure that system will go well. Any schedule tau with letters L can be transformed into a DD schedule of T or N with latency L or N less than L, which is the minimal latencies. This is one of the ways to scheduling aperiodic functions, and remember that the worst case scenario happens always if all tasks came at the same time. There's another way called force here, or earliest deadline first. Horn says that, okay, let's search for uh, for each time a new task is ready to arrive, it's inserted in the queue of the ready tasks sorted to their absolute deadline. Tasks at the head of the queue execute. If an arrived task is inserted in the head of the queue, the currently executed task is preempted. The difference between the EDF and the EDD is between the earliest due date and earliest deadline first is mainly the preemption. If you don't have preemption, they are equal. So this is executing task, you get an SR one. If it doesn't have a faster deadline, you just add it. A third one, if it didn't have a closed deadline, just add it. This one is the same, but look at the green one. This one has the earliest deadline. It will push all, preempt them, and starts to execute, and the whole queue is going to be rearranged in the middle. We can solve a problem like this. This is the task arrivals. So we have 3 tasks, T1, T2, T3, and they arrive at 0, 4, and 5. This is duration 10, 3, and 10. I don't care. So as soon as task 1 comes, I'll start executing it. And as soon as task 2 arrives, its deadline is 28, which is less than T1. Then it will preempt T1 and start executing it. When T3 comes, it will not preempt T2. It will just wait. Here, it empted T1, but T3 is not going to empty T2 because the deadline is larger. And we're going to ignore it until we finish the 3 clock cycles of T2. Then we will start the 10 clock cycle of T1, of T3, After we finish this, we'll start again to finish T1. This is how EDF runs. We have a proof that EDF optimizes or minimizes maximum latencies. Some people use another way for, actually EDF always respect RMS or rate monotonic systems. And the difference between both, that EDF is a dynamic way for scheduling while RMS is a static way of scheduling. But this is not the only way. We have another way called least laxity or least lag time first. Let's work on this and see what is the problem of this system. This is the same three tasks we had before. I'm not going to ignore or concentrate only on the deadlines, but I'm going to concentrate about the slack. If you have less slack, then you have higher priority. If you are think about this, you actually do this while studying. The closest deadline, or you know that certain task will take 5 hours. If you have 8 hours only, you will start this function. If you have another function that will stay for 12 hours, but you have 24 hours, you will always start with the one with that you cannot finish in time. So let's calculate the laxity at every single point. Here, we are going to start with T1. This is the only one we got. As soon as T2 comes at clock arrival 4, we are going to calculate the laxity. How we are going to calculate it? The deadline is 33 minus 4 clock cycles or clock slots I finished, minus 4 missing or still I have to do, then I have 23 clock cycles needed to finish this task or before the deadline, or this is the laxity I have. But think about this, the deadline of task 2 is 28, minus 4, which is the arrival time now, minus 3, because I didn't execute anything of this task, then the laxity will be 21 only. I should preempt T1, and I will start in T2. Then T3 arrives. T3 arrives, I have 33 minus 5 minus 6 for T1. Then, as the 6 is the remaining time, then it's 22. The laxity is 22. T2, 28 minus 5 minus 2 is 21. But think about T3. I arrived at 5. I have duration of 10 clock cycles, and the deadline is 29. So my laxity is only 14. So I should start in this T3. Then T3 here is going to preempt T2. Remember, in the earliest deadline first, it didn't do this. It will keep working. By the way, I'm checking the laxity every clock cycle. I'm just see here the deadline or the main changes. Look at here, still T1 is 14, T2 is 13, and T3 is 14. Now T2 got less than T1. I'm going to jump and execute 2 clock cycles. It's done, so I'll just throw it away from the queue, and I have T1, T3. Then I'll compare between them and calculate. Then now both of them are equal. How should I choose? I'll choose the one with earliest deadline first, which is the 29, and I will execute T3. But as soon as I execute this, I'll check, I'll find that T1 is less. I'll execute it here, jump for T1. T3 has less laxity, I'll execute it here, then T1, and so on. The problem here is that I go with more execution, more functions like this to be executed, and more decisions. And I keep running between different tasks, which is not good. It's not sufficient to call a schedule recompute laxity just at task arrival time. So the overhead of the schedule is higher. You have many context switches. Detects, this is an advantage. If you are going to miss a deadline, you will detect it before this, because you are going to know that a certain laxity is 0. The LL is always optimal in scheduling for monoprocessor system. The dynamic priorities cannot be used with a fixed priority OS. This is a bit software, we don't care about it. And the LL schedule requires the knowledge of the execution time. So, what if we have other constraints? For instance, we can execute T1 here, but we cannot start executing T3 until T1 and T2 are done. Actually, we're going to discuss this for constrained system or systems that is dependent on each other on the next lecture. This is we'll concentrate this on the next lecture. But think of it like this. How about sporadic tasks? What is sporadic task? I have a processor that runs over 2 gig. What do you think about the keyboard? The keyboard is considered very slow compared to the processor execution time. Then we are going to discuss sporadic tasks, the tasks that comes in every very long while, like the keyboard compared to the processor speed. To do or to model these tasks, we are going to consider it as interrupts, or we are going to consider it as periodic tasks, and we are going to check this task every single period. And this period is very large, because if the processor is 2 gigahertz and you consider and you run and you go and check if your task comes once every 1,000 clock cycles, you will never miss a key press key. So sporadic tasks are essentially can be turned into periodic tasks very easily. Thanks a lot. Concentrate next time on constraint-based system and have a good day.